Let me ask you something that seems almost too obvious to ask. What is time? You experience it constantly. You feel it passing right now, this very moment slipping into the past as the future becomes the present. Your entire life is structured around time. You remember yesterday. You anticipate tomorrow. You age, you change, you move through time like a swimmer moving through water. But here's what decades of physics have taught me. Time is not what you think it is. Time might not even exist in the way you experience it. The flow of time, the passage from past to future, the sense that moments are slipping away, all of this might be an illusion, a very convincing illusion, perhaps the most convincing illusion there is, but an illusion nonetheless. I know this sounds absurd. How can time not be real when everything in your experience confirms its reality? How can the past not be gone when you can't reach it? How can the future not be coming when you're clearly heading toward it? But physics doesn't care about our intuitions. Physics follows the mathematics, and the mathematics tells us something extraordinary. At the deepest level, time might not flow at all. Past, present, and future might all exist equally. And the sensation of moving through time might be a story your brain tells you, not a feature of the universe itself. Let me take you through the evidence. Not speculation, not philosophy. The actual physics that has led serious scientists to question whether time is fundamental or merely emergent, real or illusory, flowing or frozen. The first clue comes from Einstein. Special relativity, published in 1905, demolished our intuitive notion of time more thoroughly than most people realize. Before Einstein, everyone assumed time was universal. There was one cosmic clock ticking away, the same for everyone, everywhere. Newton called it absolute time. It was the stage on which physics played out, unchanging and eternal. Einstein showed this was wrong. Time is relative. It depends on your motion. If you're moving relative to me, your clock runs slower than mine. Not because there's something wrong with your clock, but because time itself passes more slowly for you. This is called time dilation, and it's been confirmed by countless experiments. Put an atomic clock on an airplane, fly it around the world, and when it lands, it will have ticked fewer times than an identical clock that stayed on the ground. The difference is tiny, nanoseconds, but it's real and measurable. This might seem like a curiosity, a strange effect that only matters at high speeds. But think about what it implies. If time passes at different rates for different observers, there's no single universal now. My present moment is not the same as your present moment if we're moving relative to each other. The events I call simultaneous, happening at the same time, are not simultaneous for you. We slice the universe into past, present, and future differently. This is called the relativity of simultaneity, and it's the first crack in our intuitive picture of time. There's no cosmic present moment that everyone shares. The now is observer-dependent. It's personal, it's subjective, but it gets stranger. Consider this thought experiment. You're on Earth, and your friend is on a planet 40 light years away. You're both at rest relative to each other, so you share a common reference frame. For you, there's a meaningful sense in which certain events on your friend's planet are happening now, at the same time as events here. But now imagine a third person moving at high speed relative to both of you. For this moving observer, the slice of space-time they call now is tilted. Events you consider simultaneous are not simultaneous for them. And here's the key point. Depending on which direction they're moving, their now might include events on your friend's planet that you would call the past, or events you would call the future. This isn't just a different way of measuring time. This is a different reality. For the moving observer, what you call the future already exists. It's part of their present, and what you call the past hasn't disappeared. It's still there, part of a different observer's present. The implication is staggering. If different observers have different nows, and if all observers are equally valid, then all moments must exist equally. The past is not gone. The future is not unformed. Everything, every moment, every event exists together in a four-dimensional block of space-time. We call this the block universe. In the block universe, time doesn't flow. Nothing moves from past to future. Instead, all of space-time simply is. Your life, from birth to death, exists as a complete four-dimensional structure. You don't move through time. You extend through time, like a long snake stretched across the temporal dimension. The sensation of flow, of moments passing, is something your consciousness adds, not something the universe contains. This is not fringe physics. This is the standard interpretation of special relativity taken seriously. Most physicists don't think about it much because it doesn't affect their calculations. But when you ask what relativity actually tells us about the nature of time, this is where it leads. Time is a dimension like space. Past and future are directions like left and right, and the flow of time is as illusory as the flow of space. General relativity, Einstein's theory of gravity, makes things even stranger. In general relativity, space-time is not a fixed background. It's dynamic. It curves and warps in response to matter and energy. Near a massive object, time runs slower. At the event horizon of a black hole, time nearly stops relative to a distant observer. But here's what's really bizarre. General relativity allows for solutions where time behaves in ways that seem to contradict our experience entirely. There are solutions with closed time-like curves, paths through space-time that loop back on themselves. If you followed such a path, you would return to your own past. Time travel, in a sense, is permitted by the equations. Kurt Gödel, the famous logician, discovered such a solution in 1949. It describes a rotating universe where every point has closed time-like curves passing through it. In Gödel's universe, you could visit any event in the past or future. There's no meaningful distinction between before and after. Now our universe doesn't appear to be Gödel's universe. We don't see evidence of closed, time-like curves in our cosmic neighborhood. But the fact that general relativity allows such solutions tells us something important. The theory doesn't contain an intrinsic arrow of time. It doesn't require that time flows forward. The distinction between past and future is not built into the fundamental equations. Let me turn to quantum mechanics, where the mystery of time deepens further. In quantum mechanics, systems evolve according to the Schrödinger equation. This equation is deterministic and time-reversible. If you know the quantum state at one moment, you can calculate it at any other moment, past or future. Run the movie backward, and it still makes perfect sense. The equation doesn't care which direction time goes. This is true of almost all fundamental physics equations. Maxwell's equations for electromagnetism, time-reversible. The equations of general relativity, time-reversible. The Dirac equation for electrons, time-reversible. At the deepest level, the laws of physics don't distinguish past from future. They work equally well in both directions. So where does the arrow of time come from? Why do we experience time as having a direction? Why does the past feel fundamentally different from the future? The standard answer involves thermodynamics, the second law in particular. The second law says that entropy, a measure of disorder, tends to increase over time. Systems evolve from ordered states to disordered states. Ice melts, coffee cools, eggs scramble. The universe moves from low entropy to high entropy. This gives time a direction. We remember the past because the past had lower entropy, and forming memories increases entropy. We can't remember the future because that would require entropy to decrease. The arrow of time is the arrow of entropy. But notice what this means. The arrow of time is not fundamental. It's statistical. It emerges from the fact that the early universe had extremely low entropy, and we're still in the process of entropy increasing toward equilibrium. The directionality of time is a consequence of initial conditions, not a feature of the underlying laws. Why did the early universe have low entropy? This is one of the deepest unsolved problems in physics. We don't know. It appears to be a brute fact about the initial state of our universe. But whatever the explanation, the arrow of time is derived, not basic. It emerges from special initial conditions plus the time-symmetric fundamental laws. Some physicists have taken this further and argued that time itself is emergent, that at the most fundamental level, there is no time at all. The appearance of time arises from correlations, from relationships between different parts of a timeless underlying reality. This brings me to the Wheeler-DeWitt equation, one of the strangest equations in all of physics. In the 1960s, John Wheeler and Bryce DeWitt attempted to combine quantum mechanics with general relativity. They wrote down an equation for the quantum state of the entire universe. And this equation has a remarkable property. It contains no time variable. The Wheeler-DeWitt equation is timeless. It describes a static quantum state that doesn't evolve. There's no Schrödinger equation here. No dynamics, no change. The universe, according to this equation, simply is. It doesn't happen. How can this be? How can a timeless equation describe a universe where things obviously change, where we experience the flow of events, where time seems so manifestly real? The answer that has emerged is that time is relational. Time appears when you consider correlations between different parts of the universe. Clocks are correlated with the systems they measure. Memories are correlated with the events they record. The experience of time emerges from these correlations, from the relationships between different components of a fundamentally timeless whole. In this view, asking what time it is like asking what left is without any reference to right. Time is not an absolute feature of reality. It's a way of describing relationships within reality. Different parts of the universe serve as clocks for other parts, and the correlations between them create the appearance of temporal order. This might sound impossibly abstract, but it connects to something very concrete: the problem of time in quantum gravity. When physicists try to combine quantum mechanics with gravity, they consistently run into trouble with time. The standard approaches don't work. The Wheeler-DeWitt equation is timeless. Loop quantum gravity has deep conceptual issues with time. String theory typically requires a background space-time, which seems to contradict the dynamical nature of space-time in general relativity. Many physicists now believe that the resolution to the problem of quantum gravity will require abandoning time as a fundamental concept. Time will emerge from something deeper, something more primitive, something timeless. The universe at its most basic level might be a mathematical structure without temporal extension, and time as we experience it might be like temperature, a macroscopic description that emerges from microscopic complexity. Let me give you another line of evidence. Consider the nature of physical laws themselves. Why should the laws of physics be the same at all times? Why should an experiment performed today give the same result as the same experiment performed tomorrow or a billion years ago? We take this for granted, but it's actually a profound assumption. It's called time translation symmetry, and it's one of the most fundamental symmetries in physics. Emmy Noether proved that this symmetry is directly connected to the conservation of energy. Because physics is the same at all times, energy is conserved. But think about what this means. The laws of physics don't reference time in any absolute way. They're the same at all moments. Time enters only as a parameter, a coordinate, not as something with intrinsic structure. The laws themselves are timeless. This is consistent with the block universe picture. If all moments exist equally, it makes sense that the laws would be the same at all moments. There's no privilege now, no special present moment when the laws are enforced. The laws simply describe the structure of the entire four-dimensional block. Now let me turn to perhaps the deepest question. Why do we experience time flowing if time doesn't actually flow? This is where physics meets neuroscience, where cosmology meets consciousness. And it's where I have to be most speculative, because we don't have complete answers. Your brain is a physical system. It evolved to help your ancestors survive and reproduce. It processes information, forms models of the world, and generates the experience of consciousness. Among the experiences it generates is the experience of time passing. But why would the brain generate this experience if time doesn't actually flow? Here's one possibility. The brain creates the illusion of temporal flow because it's useful for survival. Anticipating the future and learning from the past requires distinguishing them, modeling them as different. The sensation of flow might be a side effect of how the brain processes information, how it updates its models, how it generates predictions. Think about how memory works. You remember the past, not the future. This asymmetry is built into the structure of your brain. Memories are formed when entropy increases, when information is encoded in neural connections. You can't remember the future because your brain hasn't received that information yet, hasn't been causally influenced by it. But in a block universe, the future events are just as real as past events. Your future brain states exist, containing memories of what you currently consider the present. From the four-dimensional perspective, there's a you at this moment who doesn't know the future, and a you at a later moment who does. Both exist. Neither is more real than the other. The experience of time flowing, then, might be what it's like to be a time-extended conscious being. At each moment along your world line, you have memories of earlier moments and no knowledge of later moments. This asymmetry creates the sensation of moving forward. Even though nothing is actually moving, you're not traveling into the future. You're simply distributed across time, and each slice of you experiences itself as the present. Some philosophers call this the moving spotlight theory, though that's misleading because there's no actual spotlight. Others call it the perspectival theory of temporal experience. Your consciousness at each moment has access only to earlier moments, and this creates the false impression of flow. Is this strange? Yes. Is it unsettling? Probably. But it's consistent with the physics, and it offers an explanation for why our experience of time is so different from what physics tells us time actually is. Let me address some objections. The most obvious is, if time doesn't flow, how can anything change? How can there be motion, causation, events? In the block universe, there's no change in the sense of things being one way and then becoming another way. But there is variation along the time dimension. A ball at one temporal location is here, and the same ball at another temporal location is there. We describe this as the ball moving, but in the four-dimensional picture, the ball is a static world line, a path through space-time. The motion is in the geometry, not in any actual movement. Similarly, causation is not about earlier events making later events happen. It's about patterns of correlation along the time dimension. We say the cause is earlier than the effect because of how entropy works, how information flows, how records are formed. But the causal connection is just a structural relationship within the static block. This is hard to accept. Our entire way of thinking about the world is built on the assumption that time flows, that the past is fixed and the future is open, that we have choices that determine what happens next. The block universe seems to undermine all of this. But does it? Consider that even in the block universe, your deliberations matter. The version of you at this moment, considering what to do, is part of the block. Your choice is part of the structure. You still experience making decisions, and those decisions are still connected to outcomes. It's just that both the decision and the outcome exist eternally, rather than the decision creating the outcome. This connects to questions about free will, which I won't fully explore here, but I'll note that the block universe doesn't necessarily eliminate free will. It changes how we think about it. Your choices are not caused by the past in a simple linear way. They're part of a four-dimensional structure where past, present, and future are interdependent. Another objection: the block universe seems cold, deterministic, fatalistic. If the future already exists, what's the point of anything? Why try to achieve anything if it's already determined? I understand this reaction, but I think it's based on a misunderstanding. The block universe is not about fate or predestination. It's about the equal reality of all times. Your future exists, but it's your future, shaped by who you are, by your values, by your choices. The fact that it exists doesn't make it any less yours. Think of it this way. In a novel, all the chapters exist simultaneously. Chapter 10 is just as real as Chapter 1, but the characters in the novel still experience the story as unfolding. They still face challenges, make decisions, grow, and change. The fact that the ending already exists on the page doesn't diminish the reality of their journey. We might be characters in a four-dimensional story. The ending exists, but we still have to live it. We still experience it as unfolding, and that experience is real, even if the underlying structure is static. Let me return to physics for a moment and discuss one more piece of evidence. The universe appears to have had a beginning. The Big Bang, roughly 13.8 billion years ago, marks the origin of space, time, matter, and energy. Before the Big Bang, there was no before, because time itself began there. But what does it mean for time to begin? If time is fundamental, this seems paradoxical. How can there be a first moment? What was happening before time started? If time is emergent, the puzzle dissolves. The Big Bang is not the first moment of a pre-existing time. It's the emergence of time from something timeless. The fundamental level of reality might be outside time entirely, and the Big Bang is where time crystallizes, where the temporal dimension appears. Some cosmological models explore this explicitly. In the Hartle-Hawking no-boundary proposal, the universe has no boundary in time because time smoothly transitions into space near the Big Bang. There's no first moment, no edge of time. The universe is finite but unbounded, like the surface of a sphere is finite but has no edge. In this picture, asking what happened before the Big Bang is like asking what's north of the North Pole. The question assumes a structure that doesn't exist. Time is not a line extending infinitely into the past. It's a dimension that emerges from a more fundamental timeless structure. I want to end with a reflection on what all this means, if anything, for how we live. Physics tells us that time might not be what we think. The flow might be illusory. Past and future might exist equally. The present moment, which feels so special, so immediate, might have no objective significance. Does this change anything? Should we live differently, knowing that time might not flow? I don't think so. Or rather, I think the knowledge can deepen our experience without changing its basic character. We still experience time flowing, even if the flow is illusory. We still remember the past and anticipate the future, even if both exist eternally. We still love, create, struggle, and grow, even if our entire lives are frozen in a four-dimensional block. Perhaps there's even something liberating in this view. If all moments exist equally, then your happiest moments are not gone. They're still there, eternal, as real as this moment. The people you've loved and lost still exist in their time, living their lives, part of the same block as you. Nothing is truly lost because everything eternally is. And if the future exists, then your struggles matter. The better future you're working toward is real. It exists. Your efforts are part of what makes it what it is. The fact that it's already determined doesn't diminish its value. It's determined to be the result of your choices, your work, your love. Time might not be real in the way we think, but life is still real. Experience is still real. Meaning is still something we create, even in a timeless universe. Perhaps especially in a timeless universe, where every meaningful moment is preserved forever. The eternal now. That's what physics suggests we inhabit. Not a flowing river of time, but an infinite ocean where all moments exist together. We swim through it, experiencing one moment at a time, creating the illusion of flow, but the ocean is still and complete, past, present, future, all equally real, all eternally present. And somewhere in that ocean, there's a version of you reading these words, and another version finishing them, and another putting down the page and thinking about what you've read. All of them are you. All of them are real. All of them are part of the eternal structure of existence. Time is not what it seems, but you are still you, in all your moments, distributed across the temporal dimension, living your life in the eternal now.